So I want you to try one, right? So I want you to try one on here, okay? And so this is what I want you to try. And so example number 4, I think. So f of x is your arctangent x. So what is the derivative of arctangent x? It's 1 over x squared plus 1, or 1 plus x squared, right? So let me write it as 1 plus x squared. And this was problem number 1, right? So this is the first problem we did today. So now you want to integrate that and get to this part. So see if you can figure this one out, right? So we already did the first part, right? So this was problem number 1, right? So this is problem 1. So we already did that one, right? So see if you can actually integrate it and get your answer. So let me pause the recording, erase everything here, and write it out a little bit nicer. And so we have a negative 1 to the n plus 1, an x minus pi to the 2n power, all over a 2n factorial. And that is our power series. Questions? So I want you to try one. So I want you to try this again, okay? So I want you to try exactly the same thing, cosine x, but the center is at pi over 2 instead of pi, okay? So let me go ahead and write it over here, okay? So I think this is example number 7. So our f of x is equal to cosine x, where the center is pi over 2. Of simply x to the n power. Then we saw the natural log version of this, right? So ln of 1 plus x, right? So that was x plus x squared over 2 plus x cubed over 3, x to the 4th over 4, plus dot. And so as a power series, that's n equals 1 to infinity. We had it xn plus 1, right? So, but let's just use x to the n here. So it's x to the n over n factorial. What we had a while ago, right? So I'll put it an asterisk over here, was this. It's the same. I just have it shifted 1, and that's why I'm starting at 1 instead of 0. Okay, right, but they are the same power series. Right? We have one for arctangent. If I remember correctly, this one was, I think, x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7 over 7 plus dot. So it's all the odd powers. Right, so n equals 0 to infinity. It's x to the 2n plus 1 over 2n plus 1, and then it alternates signs, so it's negative 1 to the n power. Now these, we got this by using the geometric series. We didn't actually use the derivatives and the formal definition of Maclaurin to get them. So we used the geometric series to get these. Okay. But the ones we use Maclaurin definition are these. So the first one, e to the x, which was 1 plus x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, plus dot, dot, dot. So it's n equals 0 to infinity of x to the n over n factorial. Now, I don't want to go through cosine and sine, but we already did them. So cosine x, right? This one was 1 minus x squared over 2 factorial, x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, dot, dot, dot. So it only has the even powers. So it's negative 1 to the n because it alternates signs. It's x to the 2n power over 2n factorial. And then lastly, what's it, sine x? So that one was x cubed over 3 factorial, x to the 5th over 4 factorial, plus dot, 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 which is the odd powers. So it's negative 1 to the n again, x to the 2n plus 1 over 2n plus 1 factorial. Any questions on that? Note, if you go to Pearson, I posted a series sheet on there. So it's a list of tests, right? So I told you about that already. At the back of that, or sort of at the second page, is actually this list. So that list is already on there. So you don't really need to memorize them, right? So these are something we use often, okay? And we sort of based our other functions off of this one. Okay. Any questions on that? Any questions on it? Okay. So let me stop my video real quick.